Hello, prob stats, and welcome to 10.1. This is correlation and regression. We've already talked a little bit about this. We've talked about your line of best fit, and that's what we're going to use, and just do a little bit more with it and how that R value actually works. So you will need stat disk. Make sure you have your notes out, and let's go. All right, when you're looking at this here, we're going to be using pair data. So like a matched pair like we've used before. And you are going to be looking at what the correlation coefficient does and how that works with it. So, your things you need to know. We're going to be using pair data to find our correlation or our R factor. We're going to determine if there's sufficient evidence to support the conclusion that there is a linear correlation between two variables. And that's what we want to look at here. So, the definitions are correlation. Sorry about that. Okay, the correlation, there exists between two variables when the values of one variable are somehow associated. So one variable are associated with the values of the other. So there's a correlation, something is happening. Okay, a linear correlation has an R factor, and the R factor tells you how good the line actually is. All right, so let's look at interpreting a scatter plot. So when you're looking at this, we say there's a positive linear correlation. If you draw, this looks like it's in a linear shape, and it's going up. There's a positive linear correlation. If you look at the next graph, it's going down, so there's a linear correlation, and your data points are closely grouped around that line. And that's what we need. So we have a negative correlation here and a positive on the other one. If you look at this guy, there's no pattern. Like I could draw one line this way, you could draw one this way, or someone this way. There is nothing. So there is no correlation. So if you look at here, your R value is almost 0. Up here, your R value was close to a -1. And on the one above, it was close to a +1. So we like 1. So R goes between 1 and -1. And then 0 means there's nothing. Well, if you look at this guy down here, there's an R value of 0.3, so it's not good. But if you also notice, upon visual inspection, we have a parabola. If it's not a parabola, it's not a linear correlation, and we cannot use our R factor. All right, when you look through here, your linear correlation R measures the strength of the line. So how close do your data points match the line that you have, or your sample data? All right, here are all our notation. Again, N is our number of pairs. Our sigma represents sum. Don't forget that. This is the sum of x squared, which is very different than this. This here means I square the x's. So I square the x values and then I add them up. This here means I take the whole sum of all the x's and then I square. Those are very different. Don't confuse these two. The other one, you're taking the x times the y and you're adding it. R is just what we use for a sample. When you have a small p, that's what we use for a population. Okay, requirements. You have to check these. All right, so your requirements to do a linear thing, it has to be a random sample. Nothing new there. When you do a visual examination, so you look at it, you graph this, it has to look like it's sort of in a straight line, and there cannot be any outliers. So if there are any outliers, you have to get rid of them. All right, so you have to remove the outliers before you do your calculation. So you have to do the R calculation without outliers. All right, let's go here. Okay, we do have an R formula, so if you're at home you can use it. We will be using stat disk. We usually round to 3 decimal places for our R. All right, when you look at your p-value, if your p-value is less than alpha, it supports the claim of a linear correlation. The reason this is when you're in this, your null is no correlation. Whoops. And your alternative hypothesis is a correlation. Can I spell correlation today? So when the p is low, the null must go. So if the p is below your alpha, there is no correlation because that is your null hypothesis. If it's greater than alpha, then again, we have a correlation and we are happy. Okay, when we look at stat disk, we're going to look at our correlation coefficient. We're going to look for the critical values and the R value, and we'll actually graph some of that. No correlation if the R is less than the critical value. So it works just like our normal distribution graphs. Properties. I'm going to do this in a minute. Has to be between -1 and 1. We've already talked about. R does not change no matter what we do. It is not affected by the choice of X or Y, so it doesn't matter which direction I go. It has to have a linear relationship. It is very sensitive to outliers, so we have to get rid of those before we go. All right, here's our data points. So we got our data points and we want to test this. So when we look through here, we need to look, what is the key issue if these data points are test grades of a subject's before and after informal instruction? Well, if they're before and after instruction, these are matched pairs. So if this is a matched pair, because every one of these goes to an individual, I am not using a linear correlation. Okay, if these are men's scores and Y is a sample of women's scores, sounds right, but it's not. These are population means. I want to know the average of the men versus the average of the women. This is not, again, we would use population mean and not an R. Okay, if this represents math reasoning score, so if I have a math score, what's my starting salary? Now I'm comparing two different things. I'm comparing a math score, whoops. So we're actually comparing the math score to my starting salary. Those are two different X's and Y's. They are not anything else, so we are ready to go. So this, I want to know how that works, and that is a reason to use an underscore. All right, here we go. We're going to compare the consumption of chocolate. So if you eat chocolate, how many Nobel Prizes do you win? Okay, I know this is ridiculous. Eating chocolate does not lead to a Nobel Prize. Otherwise, I'd have tons of them. But this is what we're looking for. So chocolate consumption is 5, 6, 4, 4, and 5. How many Nobel Prizes are won are 6, 9, 3, 2, and 11. I want to know if there's a linear correlation between these two. Now, if I was going to do it by hand, we would do X is here for your chocolate. We would do Y for our Nobel. We would square my X's. We would square my Y's. We would take the two times each other to get your XY. Then we'd find all of those sums and we would plug it into this formula. And if we did so, we would get 0.795 for our correlation coefficient. Remember, we like 8 or higher. 0.795 isn't terrible. All right, so now we're going to use StatDisk instead. So you're going to go into StatDisk and you're going to type these numbers into your data. Okay, once you type them into your data, your first and your second column, you're going to go to Analysis. So make sure you go to Analysis, Correlation and Regression. And then you say, hey, what columns do I want? And you're going to pick 1 and 2. So 1 is going to represent chocolate, and 2, so this is going to be your chocolate, and this is going to be your Nobel Prizes. All right, and we want to evaluate this with a 0.05 significance level. So when we do that, we get an R coefficient of 0.79494, the same as we did by hand. All right, we're going to be looking at these critical values here in a little bit, and the p-value. So both of those are going to be important. I also wanted to remind you about how you wrote your line of regression. Remember, this was the slope. So that was what went in front of X, and this here was your y-intercept, which went here. So how is everything changing? So how does chocolate increase or decrease our Nobel Prizes? All right, let's use our p-value. So we have a p-value of 0.10798. Well, my p-value is greater than 0.05. All right, since my p-value is greater than 0.05, we cannot reject the null. And remember, our null hypothesis is no correlation. So since I cannot reject the null, I cannot claim that there's a linear correlation. It doesn't work. Now, let's see if we can do anything about that. Let's go down here. Now, I'm going to use the value of 0.801 for 23 pairs of data. So I'm increasing the number of data that I'm using for my chocolate and my Nobel Prizes. Okay, a Nobel laureate is just who has won them. My significant level is going to stay at 0.05. And when I type this in, was it a simple random sample? We're going to assume it is. All right, doesn't appear anything weird, but okay, I should not say that. It probably is not a random sample, so our data is not going to be valid, but we're going to do it anyway. Now we're going to actually look at our scatter plot. So we're going to type in all these numbers that we have. And we look at our scatter plot. It has a rough linear shape. Like right there, there's a rough linear shape. It is positive. There's some that are really far away, but it's not terrible. So now when we type this into StatDisk, we're going to get a correlation of 7.995. Look at our p-value. Our p-value is 0. Since our p is low, we have to reject the fact that there is not a linear correlation, so we're going to assume there is a linear correlation. All right? So there's sufficient evidence to support the conclusion that there is a linear correlation between chocolate consumption and Nobel laureates. Does not mean causation. Remember, that would be dumb, but there is a correlation. Okay, now let's look at these R values. We have critical R up right here, negative 0.4 and positive 0.4. So we have graphed this on this number line. So when you look at those graphs, this here, right here, would be rejection of the null. So that rejection means, remember the null again is no correlation. So we would reject the null at those, and we would keep the null here. Well, if you look, the R coefficient of 0.7995 is in here. So it is in the I just wrote that in the wrong spot, for crying out loud. Let's try that again. I'm sorry. So it's going to go right here, our 0.7995. I don't know why I got a 0.8. Oh, they rounded. Okay, so 0.8 right here. That 0.8 is in this here, where the rejection of the null. Since I'm rejecting the null, I do have a correlation, which means I have an R value, which means I can write the line. So there is a linear correlation. Even though this is true, that does not mean causation. Eating chocolate does not cause you to win Nobel Prizes. That's ridiculous. But there is a correlation for some unknown reason. Maybe not a good one, though. All right, variation. R squared is a proportion of the variation of y that is explained by the linear relationship between x and y. So let's look at this. We have our data values. We have our R. When we square it, we get 64. Okay, what that means is 64%. All right, so this 64% of the variation can be explained by the linear relationship. 36 of it cannot be explained. Since 36 of it cannot be explained, this is probably not the best line, but that's okay. Remember again, correlation does not imply causality. There's not a causation here. All right, errors. Correlation implies causation. We know better. You cannot do this. The other one is you cannot use data based on averages. Averages do not work in a correlation. It has to be exact data. And you ignore the possibility of nonlinear. So you did not do your visual test, and you did not look at that it cannot be a linear thing. So all those three things you need to avoid these. Whoops. So we want to avoid that these happen. Okay, I already talked about our null hypothesis is no correlation. Our alternative hypothesis is correlation. And that's what we use for our testing and for our P. All right, we're going to use a 0.05 significance level for our testing hypothesis. So we got to check our requirements. To claim there's a linear correlation, the population correlation coefficient P is different, therefore we have the following hypothesis. Okay, was it from a sample? Did you check to make sure it had a linear thing? And did you remove the outliers? And the answer is yes, we did all those. So we have to do random. We have to visually look at it. And we have to remove outliers. This part right here is going to be very important on our homework because if you don't remove the outliers, it doesn't work. So we've done our test statistic of 6.11. When we plugged in our 0, we got 0 is less than this, so we reject the null, which means we do have a linear correlation. So we can conclude there's sufficient evidence to support the fact that a linear correlation between chocolate consumption and Nobel Prize winners does exist. All right, here we go. We're going to do a linear regression line using the data from our survey comparing height to the length of your right foot, the significance level of 0.05. So pause and make sure you sort your data first. All right, make sure you're sorting by height. All right, so sort by height. And you want to go large to small. And then remove. We have to get rid of the outliers. So you got to remove the outliers. It depends on which data set you're losing. There's like roughly 5 to 6 of them, I think, on the bottom of those that you have to get rid of. So you're going to move the height with the foot because both of that data has to go away. So do that and then type those into your stat disk. Pause and get that done. Okay, I used it from our first data set, so it should be close. And when you did this, you should have removed, I think mine was the bottom 6. So when you look at your data, the bottom 6 should be gone. There shouldn't be anything that doesn't have like a double digit on it because those were outliers. They did not work well. So now we need to go to analysis. You're going to go to correlation regression, 0.05. I want my foot for the first one, my height for the second, and evaluate. Okay, when you did this, we'll look at our null. So we're looking right here at our null value of 0.00. So the null is below 0.05. So reject the null. We know we have the correlation coefficient. All right, we have the 0.05. We're going to use our critical values of plus or minus 0.287 and our R coefficient of 0.82. So now when we draw those in our p-value here, and we also can write our equation of our line from the 37 and the 3.133. So now let's go back to our data. Okay, make sure you have all your data written down. Also, let's look at our scatter plot. If you look at our scatter plot, we have a nice, fairly linear shape. It does look good, so our visual explanation is good. Later on, we're going to be looking at this residual plot, which shows us how close things match, and we kind of need to look at the shape of that. It actually looks good, but we'll talk about that later. Okay, I hope you have all your results written down. Let's go back to our notes. So when we go through this here, you should have written down what your null was. So step 1, null is no correlation. I don't like this red. And the alternative is a correlation. Okay, when we look at our stuff, oops, this is actually 1, 2, and 3. Remember those steps? 4, our alpha has to equal 0.05. 5, we know we're looking for a correlation coefficient, so we know what we're using. 6, we're actually going to start doing our work now. So we look at our critical R, and our critical R is plus or minus 0.28756. Our coefficient, our R correlation coefficient, 0.82031. So like when I graph this thing, I always like this guy. It helps me figure it out. So we have 0.28. We have negative 0.28. 0.82 is here. This is my rejection region. So this means I reject them. Let's look at our p-value. P-value is 0.000, which is less than 0.05, which means I also reject the null. Okay, this means I do have, so we have a linear correlation, which makes us happy. So now we're going to write down an equation of our line. So we have y equals 3.134x plus 37.365, which is not bad. Now when we look at this, what's explained by what? So this is 7 and 8. So now we're going to look at our r squared. And our r squared, we have 0.6729. That means 67.29% is explained. fire line, basically, for regression, and 32.71% is unexplained. So this is explaining our variation, like how far off we are. So it's not really good. We'd really like this to be higher, but it's not terrible. All right, I hope you did a good job. Make sure you do well on your homework. You're using your survey data, height to arm span and height to heart rate. Let's see if they both have a correlation. Good luck, and make sure you post questions.